Okay, this is your Chapter 20 video supplement on water pollution. First thing I want to talk to you about is water quality regulations, not something that's really discussed much at all in your textbook chapter. Um, as far as this country goes, EPA, U.S. Environmental Protection Agency, comes up with two types of regulations. So we have what's called MCLs and MCLGs. This stands for maximum contaminant levels. Once again, maximum contaminant levels. And this one is the same, maximum contaminant level goals. And the difference between these basically is the MCLs are water enforceable. And these are non-enforceable. And this is for drinking water. Okay, so you might wonder why we have non-enforceable goals. Doesn't seem to make sense. Well, first let's look at something like a carcinogen. So a carcinogen has an MCLG of 0. Okay, just by the very nature of it, something that is known to cause cancer or suspected or probably cause cancer in humans, we don't want that in our water, right? So EPA sets a goal of 0. However, for each of the chemicals that might be on this carcinogen list that have a 0 MCLG cannot possibly have an MCL of 0. And think about that. The reason is because of this. There's no way to prove that there's 0 amount in the water. So you might say to yourself, okay, we'll just take a water sample and measure the amount in there. And if it's 0, well, no. If it's 0, that just simply means that is not detectable by whatever instrument and method you're using. Keep in mind we are limited by science. There are some limits to what we can detect, what we can measure. So while I might take a sample and tell you, hey, there's no chemical X in here, as far as we can tell, the way it's typically reported by these companies that do this measuring or labs like ourselves that do this type of thing is we'll say, well, it's below our detection limit. That's all we can say. And that's why they're non-enforceable. So the MCLs are the enforceable ones that EPA puts out there that, treatment plants have to abide by and have to submit reports to show that they're reaching those standards. But MCLGs are not enforceable. So what you have is, kind of those goals, what we'd like to achieve. And some chemicals don't have MCLGs of 0. They have higher ones. And so ultimately, sometimes the MCL gets lower and lower as our technology gets better approaching that MCLG. So that's the difference between maximum contaminant levels and MCL and maximum contaminant level goals. Next thing I want to talk about oxygen depletion, because this is something that's important and it's discussed quite a bit in your book. So there's a couple ways that can come about, but let's talk about why it's important. Of course, we want oxygen in our waters because our fish and organisms in water depend on oxygen. And if your oxygen levels are low, then fish start to die off. That's a food supply. That's the food chain. That's the ecosystem that is negatively affected. So obviously, we want to have a healthy ecosystem with lots of oxygen in the water. So there's two ways in which oxygen can be depleted. One is by eutrophication. And another is by oxygen-demanding wastes. Now, ultimately, the result is the same. The oxygen gets depleted or is to really low levels, and that affects the fish and the ecosystem. But the way in which they come about are slightly different. So eutrophication, and we draw a distinction in your chapter and say cultural eutrophication is what, is eutrophication that we have induced, humans have induced. Eutrophication is actually a natural process that happens in the environment, but a much slower than cultural eutrophication. Excuse me. So with eutrophication, as you should have gotten from your reading, is basically you have this, plant nutrient, this limiting nutrient that gets into the water. And typically the limiting nutrients, what we mean by that is nutrients that typically plants don't have enough of to grow. And specifically now we're talking about, aquatic plants like algae, okay? Now plants in general are limited by basically two elements, nitrogen and phosphorus. But here we're talking about water systems, so we're interested in these algae. And they're limited, and their growth is limited. Now, these types of plants are just like bacteria. They're small, and they multiply really fast. So as long as you have a normal body of water with not much nitrogen or phosphorus, that keeps them in check. All the other stuff that they need to build and grow is there, but they don't have enough nitrogen and phosphorus, so their numbers are kept low. Now, of course, you have let's just say a lake that's next to a golf course or next to a farmland, and you're getting a lot of nitrogen and phosphorus running off. All of a sudden, these algae that are in the water have plenty of this limiting nutrient, and they grow uncontrollably. And you've seen pictures, I'm sure, and you can just Google eutrophication and look at pictures. There's some in your book. But you get these blankets of green growth across the top of the lake, which causes problems. It keeps sunlight from penetrating. Okay. But the big problem comes from as those algae die, because they have a short lifespan, just like bacteria. As they die, bacteria feed on their dead bodies because that's just they're little packets of great treats for them, right? Because they're just organic, nutrients, high-rich materials of food for them. So the bacteria break them down, and of course, bacteria go through respiration. Talked about that early in the class, in the course. Respiration, of course, is the same thing you do. You basically use up oxygen, right? You produce carbon dioxide. So what you're doing now is the bacteria degrading the algae is what depletes the oxygen. With oxygen-demanding waste, you're really just eliminating that first step. It's not the addition of nutrients. Here, you're just releasing, stuff like sewage into the water, which is high organics, easily degraded by bacteria, a great food source for bacteria. So ultimately, what do? They simply feed on that sewage, and the same thing happens. You deplete the oxygen. Now, one thing we did see in our book is a graph of an oxygen sag curve. And basically what you have is oxygen on this level, on this axis, and it was drawn more in a pictorial format. And this down here could be time, or it could be distance downstream if it's like a stream. And you see something like this, right? Where this point right here is where that organic waste has been added. Okay, this would be your healthy, normal background level of oxygen, and then the oxygen drops and it recovers eventually because basically all that waste has been broken down and the water re-aerates with the air and the mixing and all of that. So the question is how much waste you add is going to determine how much oxygen is depleted, how low it gets, but also how far downstream and how long this lasts. So you might be able to calculate actually how far downstream before the water actually returns to its normal oxygen level. And what you typically see in this area is a fish kill. Okay, so now I want to mention a little bit about heavy metals, because your book, once again, doesn't really talk much about that. And I'm not going to say much here. I just want to make you aware of a couple of the key metals that are important. We say heavy metals, just such a general term for certain types of metals that are toxic, but things that are commonly in this list are things like mercury, lead, cadmium, chromium. Arsenic's actually a metalloid, so that's what I mean by heavy metals kind of include basically just toxic metals of a certain molar mass. And sometimes they define them in terms of density, but just gives you an idea. So some of the sources of these, mercury comes from burning coal. Lead we used to use in leaded gasoline. Cadmium is common in batteries and paints. Chromium's used in electroplating and leather tanning. Arsenic's actually not used that much, but it occurs naturally in coals and different ores and actually creates a lot of problem with groundwater pollution. And as far as the effects of these, well, remember, we had a whole chapter on human health effects, and we talked about metals, and we said a lot of these metals have an affinity for a certain element in the body, which might be part of a biomolecule, which can then bond to that biomolecule and then render it kind of useless. And one of the things we did talk about is the element sulfur in enzymes. So that's just to bring back that earlier material we talked about, that some of these heavy metals have an affinity for these, and if they're in a biomolecule, that can create a lot of problems, and that's where some of these toxic effects can come from. The next thing I want to touch on is these toxic organics, and when we talk about toxic organics, there's a whole different classes and slews of different organics. I mean, there's organic solvents that are used. There's different types of pesticides that we use. So, and then there's, materials that are used in like as dielectric fluids and things like this. So there's lots of different options for organics to get into the environment. Things we use in manufacturing and processing of materials, whether we're producing paints and things like that. So lots of options for organic chemicals to be out in the environment. And there is a group of what's called persistent organic pollutants, and there's 12 of these, and that stands for persistent organic pollutants, and they're called the Dirty Dozen. Whoops, DIRTY dozen. And this was a group of 12 chemicals decided on internationally. This is a worldwide list. And EPA is part of that. Of course, the United States is part of that. And if you look at this list, a lot of them are insecticides. And because we're adding these things to our environment. Now keep in mind, there's lots of organic and chemicals that are used in manufacturing processing that often don't wind up in the environment. So they're handled in a proper way, they're recycled, they're reused, they're disposed of properly. But insecticides obviously is an ideal chemical in which we are, dispersing in our environment, or any pesticides are. But insecticides tend to be particularly problematic because many of them are things like neurotoxins or endocrine disruptors. They're designed to mess with the insects, so if they're in their environment, we're being exposed to them also. And of course, one of the infamous ones, of course, is DDT. And this, along with many of the other ones on this list, are the ones that kind of arose during the 70s when we had the formation of the EPA and Rachel Carson's Silent Spring that stimulated the entire environmental movement. So these were the chemicals that caused a lot of problems with, getting into birds of prey. We talked about bioaccumulation and biomagnification already. These are the ones that were famous for that, and led to eggshell thinning and depletion or degradation of the bald eagle population. So a lot of these have very similar structure, and a lot of these actually have been banned in this country, and we've replaced them with other ones that are less persistent, but tend to be a little bit more toxic in terms of acute toxicity, which is something we talked about in the hazards in human health section. Next, I want to talk about treatment of water, and one thing we saw in our book was treatment of wastewater. And the book talks about primary versus secondary treatment of wastewater. And primary you can think about as basically kind of physical operations to remove a lot of that kind of floating and stuff that settles, that's bulk waste, if you will, bulk stuff that has to be removed. Secondary is designed to reduce the BOD. And if you look at BOD, I talked about in the slides, it's in your chapter, but it's kind of nestled in there. You have to look a little hard. It's not really highlighted. It stands for biochemical oxygen demand. And that is those oxygen demanding organics. The idea of secondary is to reduce that. And so typically we take wastewater through primary and secondary treatment, then also a tertiary treatment your book doesn't really talk about much. This is kind of a final polishing step, and that will vary tremendously depending on the type of water and the area you're in and what the regulations are. Primary and secondary, while there's different options, they're all very similar in terms of what different wastewater companies do and different municipalities do. And then ultimately, we treat drinking water. And a lot of what we do for drinking water is kind of specialized steps. And that is, it's almost very similar to what's done for tertiary only, a group of tertiary things. You might think of it like that. We don't call it that because it's not wastewater treatment. But if you're familiar with things like reverse osmosis, carbon adsorption, if you have a water pitcher at home, like a Brit or a Pure, that has a little filter you put in it, that's basically filled with a carbon material that has a great absorption capacity, and it'll remove lots of things like organics and heavy metals. Reverse osmosis is just pushing water through a membrane to filter things out. So all different types of things you can do to treat your drinking water. For drinking water, obviously, we don't have big bulky wastes in there. You're pulling up groundwater or surface water. And if you're pulling in surface water, yeah, you got to remove sticks and stuff like that. Pulling up groundwater, really, you don't have a lot of bulk waste to remove. But you don't have a lot of BOD in this water, so it's not really a primary, secondary, tertiary thing. It's kind of like very specialized. Every municipality, every company does it differently in terms of how they go about treating their drinking water, and it involves multiple different steps. Just depends on what each group decides to do. So just to remind you, reverse osmosis is an option. Things like carbon adsorption. And you can just use things like filtration. There's just different things you can do to clean up your water, basically. Okay, so that brings us to the end of the video and a summary of the things you should get out of this video and out of your reading and out of your worksheets and all that. So you want to be comfortable with the causes and effects of water pollution, and specifically focusing on point and non-point source pollution. Know what those definitions are, know what those some examples are. Some of the problems we saw, oxygen sag curves and eutrophication, are two of the big ones. There's lots of other things talked about in your book. It talks about the problems with oil pollution in oceans, red tides, various things like that. Ultimately, the book chapter ends with kind of reducing water pollution, things you can do, and one of the things we do is treat our water, so primary and secondary sewage treatment, specialized treatments for drinking water, but there's also other things like how we can, eliminate ships from dumping waste and stuff like that in the ocean. We can use double hull ships to protect against oil leakage. We can require better monitoring of landfills and things like this. So there's lots of solutions listed in your book and options for things that we can do to improve our water quality. And that concludes the video.